Hello, my wonderful AP Chemers. Hope you're having a wonderful day. We're going to start chapter 7, which is periodicity or periodic trends. So, in a polyelectronic atom, that means an atom that has more than one electron. Two forces are acting on the valence electrons. So if you look at hydrogen, for example, hydrogen only has one electron. It is monoelectronic. It only has one electron. So the only force that's acting on that electron is the attraction between the positive nucleus, the protons in the nucleus, and that negatively charged electron. There's an attraction here. And so that has to do with the nuclear charge, or the number of protons. So the protons have an attraction to the electron. Now, let's say you have something like lithium that is polyelectronic. That means has more than one electron. You have two forces now. So here are your, there's your 1s. And so you have two electrons here. And then I'm going to do it a different color. Let's make it blue. Here's your 2s. And there's an electron there. So if you look at this valence electron and what forces are acting on it, there are two forces. So you have the force of attraction between let's just do it in blue. So you have the force of attraction between that electron and the nucleus, positive versus negative. And then you also have something called shielding. So there is a repulsion between those electrons. If you remember last year, I kind of compared this to football, and I said, imagine that, this is the quarterback. Let's call it quarterback. And this is the defense, right? The defensive line. And then this is the offensive line. And so that electron is really attracted to the nucleus, right? It wants to get there because there's an attraction. But those electrons are kind of blocking it, shielding it. So in the same way, like the defense is trying to get to the quarterback, but the offensive line kind of protects that quarterback and kind of prevents the defense from getting to it. And so the net between those attractions, the attraction to the nucleus and then the repulsion or shielding by the inner electrons results in a net attraction total. That's why those electrons don't fly away. If the net was not an attraction, then they would just fly away. So them staying there tells us that the net between that attraction and that repulsion is a smaller attraction. And so that's what we called Zeff last year, the effective nuclear charge, or Zeff. So it is the nuclear charge, which is the Z actual. Remember, Z is the number of protons. So the attraction, because of the protons, minus the repulsion of the inner electrons, or the shielding. This year, instead of calling it Zeff, we are going to call it the net Coulombic attractions between the nucleus and the valence electrons. So it's kind of a long name, but College Board loves this phrase, the net Coulombic attractions. They love Coulombic attractions. Coulombic attraction just means positive, negative attraction, or negative, negative repulsion. If it's attraction, obviously positive and negative. And so the net between all these is called, last year we called it Zeff. Now we're going to call it the net Coulombic attraction between the nucleus and the valence electrons. Now that Coulombic attraction, or Zeff, decides all kinds of different properties of atoms. Remember from last year, we kind of showed all kinds of different properties like atomic size, electronegativity, ionization energy, all these things. Okay, so let's look at potassium, for example. So potassium, we have, let's do it in orange. We have a bunch of electrons here, right? Bunch of electrons here, bunch of electrons here, electron there. So what we're interested in is all these properties are caused by the net attraction between this valence electron, it's just the valence electrons that we care about, not the rest of the electrons, just the valence electron, and the nucleus. And so there's attraction here between the two because this is positive and this is negative, but then there is repulsion here, right? All of these are shielding that electron from the nucleus. So the farther out we go, the higher the energy level we go, the more shielding we experience, and therefore the less the net Coulombic attraction between the nucleus and the valence electron, or the less Zeff is what we called it last year. So let's look at the Zeff trend in the periodic table. So as we go across the periodic table, Zeff, or the net Coulombic attraction between the nucleus and the valence electrons, increases. Why does it increase? Because if you think about it, as you go across and as you go down the periodic table, the two factors increase, right? We have more electrons to repel, but we also have more protons to attract. So which one wins? Well, it depends on the placement of those additional electrons, because the protons will be in the nucleus no matter what. Any additional protons will be in the nucleus. But additional electrons, sometimes they're added in the same energy level, in the same shell, and sometimes they're added in different energy levels. So as you go across, you're adding more protons, and yes, you are adding more electrons, but those electrons are in the same energy level. So if you look back at our diagram here, let's say this was not potassium. Let's say it's an, what's the next element? Calcium. So let's say it was calcium. Whether you have one electron here or two, it doesn't really affect the shielding, right? The shielding is the blocking or the repulsion of the valence electrons by the inner electrons. And so if it's in the same period, yes, we're adding, more electrons, but those electrons are not repelling each other too much. If we were adding energy levels, then yes, you'd get like more and more repulsion. But if they're in the same energy level, it really does not matter that much how many electrons are there. So those extra electrons don't really matter, but yet we are adding more protons, and so that attraction is gonna increase. And so that's what this is saying, really. Additional valence electrons are in the same shell, so they experience minimal additional shielding. The extra shielding is very little, is what this is saying. At the same time, you have higher nuclear charge, you have more protons, and so the net attraction would get stronger. Now let's look as you go down a group. So as you go down a group, yes, you're adding more and more protons in the nucleus, but now you're adding more and more and more energy levels, right? So you're adding these inner electrons. So now you have your valence electrons here. You're adding more energy levels, so a lot more shielding. So yes, there are more protons, but those extra electrons are in higher energy levels, and they are experiencing a lot more shielding by those inner electrons. And so now your net attraction lowers or decreases. So let's look at the explanation. Higher nuclear charge, yes, we have more protons, but the valence electrons in the higher energy shells, so the shielding increases by a lot. And so therefore the net Coulombic attraction between the nucleus and the valence electrons decreases. Now, the way that these explanations are written, these are totally fine, right? You look at both protons and electrons. But if you want to shorten your explanation, you can kind of just look at one aspect of it if you want when you're explaining it. So as you go across, which one's more important? Because you're adding more electrons and more protons. Which one's more important? The protons are more important. So if you just tell us, as you go across, you have more protons in the nucleus and therefore the attraction increases, that's good. That's enough. As you go down, yes, you're adding more protons and more electrons, but which one is having a higher effect? Well, it's the addition of the electrons in higher energy levels. So you can ignore this part and just tell me about the extra electrons, and that would be good as well. So if you want to give the whole explanation, that's fine. If you want to just give the main reason, that's fine as well. Okay, and really once you have that explanation, you can really explain any other trend from there. So let's look at size next, atomic radius. So if you look at the atomic radius, it's defined as the distance between two nuclei. So if I have a nucleus here and another nucleus here of a neighboring atom, and I look at that distance, take half of it, that's going to be the radius of this atom, right? So it's half the distance, I should say half the distance between two nuclei, and it's measured, I mean, you know, the atoms are really small, so it's measured in nanometers or picometers or angstroms. Angstrom means 10 to the negative 10. You don't really need to know that, but just it's common that it's measured in angstroms. Pico, of course, is -6. Nanometer is -9. So as you go across the period, the size decreases. Remember the one-armed snowman that we drew last year? So as you go across, the size decreases. As you go down, the size increases. Let's think about why that is. Well, it all has to do with Zeff, or the net Coulombic attraction between the nucleus and the valence electrons. So as you go down, the well, let's go across first, because across is first. So as you go across, you do have extra electrons, but they're in the same energy level, so there's not much extra shielding there. What's more important is you have more protons in the nucleus. So as you go across, more protons in the nucleus increases that net attraction. So valence electrons are in the same energy level, which means no extra shielding or minimal extra shielding. The higher nuclear charge having more protons, so more attraction. So the net Coulombic attraction between the nucleus and the valence electrons goes up. And therefore, the valence electrons, because there's much more attraction, the valence electrons are held tighter. And so the space that the atom takes is smaller. The radius gets smaller because there's more attraction between the nucleus and the valence electrons. As you go down a group, you can tell that it's getting bigger. Why is that? Well, as you go down, your extra electrons are in higher energy levels. And so there's more and more shielding between the valence electrons and that inner core electrons. And so the Coulombic attraction decreases. There's less attraction, so the nucleus doesn't hold the valence electrons very tightly. They're held looser, and so they're farther away and a bigger size. So valence electrons occupying higher energy levels, so shielding increases. The net Coulombic attraction between the nucleus and the electrons decreases, and the valence electrons are held looser. All right. So if you're asked about two different elements that are in the same period or the same group, it's pretty easy to tell which one's larger in size, right? Just based on this trend. But what if you're given a whole bunch of different elements? Then what do? So what you do is you look at a periodic table, and you pick, so if this was my periodic table, for example, right here, you pick the corner of the periodic table that has the largest sizes. And so in this case, it would be this corner where like francium is. You pick the corner that has the smallest sizes. So since we're looking at atomic radius, this would be the smallest. And you look, you say, oh, it's decreasing order. So that means from highest to lowest. So we need to go this way on our periodic table. And that will give us the different sizes. Now, if you are comparing two of them that are the opposite way, like this way, then which one matters more? Because one way you're decreasing and one way you're increasing. And so when it comes, it depends on what property you're looking at, but when it comes to size, which one do you think would matter more? Which period or which group? Well, it would matter which period it's in, because an extra period means an extra energy level, so much farther away, so larger size, right? And so anything I shouldn't say anything, but most elements in the third period are going to be larger than most elements in the second period, right? Or almost all of them. So, so I'm going to pull up a periodic table here, and let's look at the elements that we have to compare. Remember, this is the largest corner. This is the smallest corner, and we're going decreasing size, so from largest to smallest. So let me circle all the ones that we need to look at. So we have aluminum, boron, carbon, chlorine, potassium, sodium, and then fluorine. All right, so based on going this way, remember we said we're going to go that way. The first one that we see is potassium. So potassium is the largest one. Next would be sodium, aluminum, or chlorine if we're going up, right? So out of these, the biggest one would be sodium. And then we get here aluminum. And then the question is, do I go boron? Do I go chlorine? You probably want to go chlorine when it comes to size, because chlorine is in the third energy level, whereas all the other ones are in the second energy level. So you want to pick chlorine because it's largest. When it comes to size, the period matters more. And then my last few boron, then carbon, and then fluorine would be the smallest. So when you're given a lot of these, just use a periodic table and go from one corner to the other. All right, let's talk about ionic radii. So ionic radius, just like atomic radius, is half the distance between two nuclei. So this one is half the distance between nuclei of two ions. Half distance between nuclei of two ions as opposed to two atoms. Also measured in any length units, really, usually nanometers or angstroms. Okay, so let's look at cations first. So if we have Fe versus Fe2 plus versus Fe3 plus, which one is the largest, which one is the smallest? Well, in general, the cation is smaller in radius than its neutral parent. So out of these, Fe3 plus would be the smallest, then Fe2 plus, and then Fe. Why is that? So when you have a positive charge, a positive ion, that means it has lost some electrons, right? Lost some valence electrons. So when an atom loses the electrons, the remaining electrons will experience less mutual repulsion, right? So if we had a bunch of electrons there and then I lost some, I have fewer electrons left. And so there's less repulsion between those fewer electrons. You still have the same number of protons, so that's still the same, that attraction is still the same, but the repulsion is less because there's less electrons to repel each other. And so as a result, the net attraction increases, right? Because the protons are the same, there's less repulsion from less electrons, and so the net, the Zeff, or the net Coulombic attraction between the nucleus and the valence electrons gets stronger, the attraction gets stronger, and so the size gets smaller. So a cation is smaller in radius than its neutral parent. Now, in addition, sometimes this applies, not all the time, but sometimes if you form a cation, you lose a complete valence shell of electrons, and that also decreases the size. For example, if I have sodium versus sodium ion, this one is smaller. If you were asked why, you can explain it this way. You can say, well, this one has the same number of protons, but yet it has less electrons, and so there's less repulsion, so the net attraction is stronger, and so it's a smaller radius. Another reason you can give is, if you look at the electron coefficient, this is 1s2, 2s2, 2p6, 3s1. This one is 1s2, 2s2, 2p6, right? Because you lost that positive charge means you lost this valence electron. Well, look at that. The valence electrons here are in the second energy level, whereas these are in the third energy level. So because you lost the electrons in that third energy level, you have less energy levels now, and so those, of course, are going to be closer to the nucleus, and the size will decrease. Now, just be careful that a lot of ions, when it comes to positive ions, this will be true, but not always. So on one of the AP exams, they had to actually compare between Fe2 plus and Fe3 plus. And so in this case, you can't really use this argument of losing a valence shell because they both have the same energy levels. So, or occupied energy levels, I should say. So just be careful of that. So out of these, Fe3 plus is the smallest. Fe is the largest. Fe2 plus is in the middle. Your explanation would be because of this right here. So you'd say that Fe3 plus has 3 less electrons than neutral Fe. Fe2 plus has 2 less electrons than neutral Fe. And so the less electrons you have, the less repulsion from electrons, the stronger the net Coulombic attraction between the nucleus and the valence electrons, and therefore the helder those electrons are, the tighter those electrons are held, or the smaller the radius. Let's look at anions. So anions are negatively charged, of course. And so if we compare between, oops, I keep doing that. I don't know why. If we compare between, let's say, oxygen and oxide ion, an anion is larger in radius than its neutral parent. Why is that? Why would O2 minus be larger in size than neutral oxygen? Well, it's kind of the same argument as the top one. So having a negative charge means you've gained electrons. Same number of protons still in the nucleus, but you've gained more electrons, and therefore you have more electron-electron repulsion, and so the net attraction between the nucleus and the valence electrons gets less, gets weaker. So when an atom gains electrons from an anion, the extra electrons will cause more repulsion, and as a result, the valence electrons are held looser, net attraction is weaker, and so the anion is larger in size than its neutral parent. So if we were to compare these here, C4 minus would be the largest, followed by C2 minus, and then neutral will be the smallest. And you'd use this reason here. This has 4 extra electrons, so more repulsion, so less attraction between the nucleus and the valence electrons. All right, so if you look at these, or these, when we were comparing them, we were comparing all of these have the same number of protons. They just have different number of electrons, right? Here, they also have the same number of protons, just different number of electrons. So let's look at this set here. How can we compare these? Because they all have different number of protons. So how are we able to compare these? It tells us that we want to rank them in order, in increasing order of radius. But how can we compare these? They have different protons. Anybody? Think about it for a second. For those of you who figured it out, good job. They all have the same number of electrons. Look at all of them. They have the same number of electrons. So neutral sodium has 11 electrons, right? But lose one of them has 10 electrons. Magnesium has 12 electrons when it's neutral. 2 plus means it lost 2 electrons, so it also has 10 electrons. Aluminum has 13 normally when it's neutral. 3 plus means it lost 3 electrons, so you're left with 10 electrons. How about carbon? Neutral carbon has 6 electrons. We're talking about valence electrons here, not just total number of electrons. This is valence electrons. So carbon has normally 6 valence electrons. 4 minus means it gained 4. So 6 plus 4 is 10. Nitrogen normally has 7. 3 minus means it gained 3. So 10 electrons. Oxygen normally has 8. 2 minus means it gained 2. And neutral neon has 10 valence electrons. So all of them have the same number of valence electrons. Therefore, we can compare between their sizes. So in order for you to compare between ions, they either have to have the same number of protons or they have to have the same number of electrons, one or the other. So since they all have the same number of valence electrons, what's the difference? Well, the difference in this case is the protons, right? We just said they're different number of protons. So let's see how many protons they have. Sodium has 11. This one has 12. This one has 13. This one has 6, 7, 8, and 10. This is the number of protons. So we're doing increasing orders. That means the smallest to the largest. So which one's going to be the smallest? Which one has the strongest attraction between the nucleus and the valence electrons that it gets a smaller size? Well, that would be the one with the most protons, right? 13 protons to pull those 10 electrons. So aluminum 3+ would be the smallest. Not just aluminum, aluminum 3+. Okay, what's next? Would be magnesium 2+. And then sodium. And then neon. And then oxide. Oops, this is just neutral neon. And then nitride. And then carbide. That one would be the smallest. Oh, sorry, largest. I'm so sorry. Because the carbide ion has only 6 protons to pull in those 10 electrons. So this one would be the largest, not as much attraction. This one's going to be the smallest in size because there's lots of attraction between the valence electrons and the nucleus. See you guys next time.